All right, IB Physics, hello. So today I'm going to go over a couple of different things about astronomy. I'm going to talk about some astronomical objects and astronomical scales. And I want to start off with this warm-up question. So the Milky Way has about 200 billion stars in it. Billion with a B, that's a lot. And if each star were represented with a rainbow sprinkle, how many school buses would you need to have all of those 200 billion rainbow sprinkles? So if you filled up the school buses, what do you think? One school bus? Three school buses? 100 school buses? Well, uh, 200 billion is a lot. It would take 15 school buses. And most of these stars in our Milky Way galaxy, and again, that's the galaxy we live in, would be in the bulge or the center part of the Milky Way. And there are a lot of stars in our galaxy. But the thing is that our galaxy is not the only galaxy in the universe. There's like 200 billion other galaxies. And so it's really hard to get a scale of things. This video we aren't going to view in this little video. We usually do a little sorting activity in class, but we're not going to do that. You already did that with that little quiz. But we are going to talk a little bit about some common vocabulary. So I want to talk about some stellar distances. We're going to do some calculations in distance learning, not as many as we would be doing in normal class. But it's really useful to know what these different stellar distance terms mean. So one term is called an astronomical unit. It's the distance from the Earth to the Sun. Its actual size is in your IB packet. It's 93 million miles, if you would prefer to have miles instead of meters. Why would you want miles? And so the Earth is obviously one astronomical unit because we define the astronomical unit away from the Sun. Jupiter is about 5 AUs from the Sun, and like Pluto is, I don't know, 10. Don't quote me on that. You could Google it. Then we have light years. You've probably heard of those before. And that is the distance that light would travel in 1 year. So, you know, light goes 3 times 10 to the 8 meters per second. So then if you're like, well, 1 year worth of seconds, how far will it go? Well, 9.46 times 10 to the 15 meters is how far it would go. And this is used really commonly. The sun is 8.3 light minutes away. So that's like a light year, except how far light will go in a minute. And the closest star to us, called Alpha Centauri, is 4 light years away. So just to give you a sort of sense of scale of stuff. Parsecs, which you have probably heard before, maybe in some sci-fi context, are actually a unit of measurement. And they're based on this parallax idea. Parallax is the phenomenon of being able to see in 2 dimensions. You have 2 eyes, and so one eye gets a different view of the world than the other eye. If you close your eyes like back and forth, you'll notice that the image you see sort of shifts. And the parsec is based on this idea of parallax, except instead of your eyeballs, it's about the size of the distance of the Earth to the Sun. And anyway, we're not going to get into that, but it is 3.26 light years is what 1 parsec is. So when you hear someone talking about, oh, that's a couple parsecs away, they mean it's maybe 10 light years away. So speaking of distances, you know about our solar system. If you played with the Moon is a Pixel from last week, it's really fun. If you haven't, I very much enjoy it. That has a really good sense of scale. But here we have just the distances scaled out. Oh, look, we can check. I was wrong. Pluto is 40 astronomical units. That's much further than I remembered. Must have gotten further away, right? And so, you know, your planets, probably you've heard of those before. We're not going to get super into them, but in the next assignment, you can totally get deep into them if you want to. Here's a fun trivia fact. If someone asks you, what is the closest planet to the Earth? You might be like, well, the closest planet to the Earth is Venus. That's a really good answer, right? Because in terms of the order of the planets, that's the closest planet to us in terms of its distance from the Sun and our distance from the Sun. But a hilarious fact of the way planets orbit, which is in big circles, is that the Earth right here is actually on average closest to the planet Mercury. On average, keyword, on average. Because Mercury is very, very close to the center of the Sun. It's just kind of a funny trivia thing that people try to use to make you think. And I thought it was kind of interesting. So we've got our planets. And again, our solar system here, we live at 1 AU, 1 astronomical unit, or 93 million miles away from the sun, or 1.94 times 10 to the 11 meters. I hope I remember correctly. You can go check if I didn't. And solar systems can be pretty darn big. And in fact, ours has some other things besides planets in it. We have asteroids. You've probably heard of those before. They're just rocks that are just chilling out. When a solar system forms, all of the sort of matter and gas and dust and stuff sort of coalesce around their star due to the gravitational force pulling them together. And so asteroids are just leftovers that didn't ever get to become a planet. And you've probably heard of the asteroid belt. It's not really, it's actually mostly empty space, but here it is between the orbit of Mars and Jupiter. We think that it probably was stuff that was tried to be a planet but failed. And then there's these things called comets. You've probably heard of those. They're snowballs of frozen gas and rock and dust. My physical science students have occasionally made comets at the end of the year because, again, they're just snowballs of frozen gases like carbon dioxide and water and dust. And while they're not really able to support lives themselves, they might have brought water and organic compounds like amino acids to the Earth because they're one of the bodies of stuff that has water in them in our solar system. And they live out here on this thing called the Kuiper belt. Kuiper Edgeworth belt. Most people just call it the Kuiper belt. That's how you say it. And that is way out here, sort of around the orbit of the dwarf planet Jupiter, Mizgats. Whoa. The dwarf planet Pluto. I'm with it. I'm not alone too much. And comets are really cool if you ever get a chance to see one. 2061 Halley's Comet is coming back. They have very predictable orbits, and so we're able to say, aha, a comet will be coming, and then look at it. And what you're seeing is the comet ice ball thing is right here, and that reflects sunlight really well. And then, because it's now closer to the sun than it usually is, it gets this tail, which is actually its ice ball crap melting off of it. And there's one tail, the comets actually have two tails. There's one tail that's ice ball crap melting off of it, and there's another tail of ions that are ions streaming off of it. Anyway, pretty cool though. And if you ever get a chance, they're really awesome. I have seen a couple of comets in my lifetime. And Halley's Comet is one that is very bright and very lovely. So in 2061, when we can actually talk to people again and see them in real life, you should definitely check out Halley's Comet. The next thing in our solar system is this region called the Oort cloud. And so the Oort cloud is just beyond the Kuiper belt. And it's where there's crap sort of spherically around our solar system, as it says here. And there are some comets that do live out here, but mostly this is stuff that's just sort of like leftovers of the early solar system. So then we go out further away from our solar system and we get into the neighborhood of our galaxy, and there's other stars with other solar systems. We learned about some of them last year when we dug into the exoplanet project, where you really started thinking about, well, how do you understand planets orbiting stars and understand gravitational forces? There are stellar clusters. Clusters are stars that are actually stuck together. And then there are constellations. Those are just stars that look close together from Earth. So they aren't necessarily actually close together. They are not gravitationally bound constellations, but they look close together. And then there are these things called nebulas, and those are pretty great. We'll talk a little bit more about them. So the two types of star clusters, we've got open clusters. Down here is an open cluster that's really famous. It's called the Pleiades. You can see it in the winter here in Minnesota. It's really pretty. You can see it with the naked eye. And open clusters are grouped together. So here is a little drawing of the Milky Way galaxy. Here's an open cluster. They're grouped together stars, and they're born from the same nebula. So they're hanging out together because they were born in the same place. Then there's these things called globular clusters, and these are actually kind of mysterious objects that we don't totally understand, but many like other galaxies that we look at that have them as well. And globular clusters are kind of like, if our galaxy is a pancake, which it is, it's a flat circular object. Globular clusters are kind of like the blueberries you maybe put on top of your pancake. They're not in the central disk of the galaxy, and they're really old, like very confusingly old. So here is a very pretty picture of a globular cluster. You have to use a telescope to be able to look at these, but through a telescope, they are actually really pretty, sort of fuzzy, kind of like you can sometimes make out some of the stars. It's very cool to look at. Then we have, like I said, these objects called nebulas, or nebulae, if you're going to say plural correctly, which apparently I am not. And they're clouds of gas and dust, and there's two different types of, actually there's technically three different types of them. So there are some nebulas that are the birthplaces of stars. And so that's where gas and dust sort of merges together to form new stars. So this is the Orion Nebula. It's the best nebula. Okay, I don't know if you can say, I'm going to say it's the best. It's in the constellation Orion. It's in Orion's sword, and it looks amazing. So this is a picture. It wouldn't look quite this amazing to your eyeballs through a telescope, but it looks pretty darn cool through a telescope. And so here there are little baby stars being formed right inside there. Aren't they cute? OMG. And so those are stellar nurseries. It's one type of nebula. Then we have these other nebulas that are the graveyards of stars. So this is the Crab Nebula. It is the leftover of a supernova explosion that actually occurred in, like, I don't know, the year 15 something. You can look it up. Humans recorded it. And in fact, we've looked at that location in the sky, and now there's this nebula there. So this is like a star that went supernova. We'll learn more about that next week. And then this is a star called a nebula called a planetary nebula. You can see the star down in there. This star is a white dwarf. And this star is also dead, except instead of having an exciting explosion, it's kind of just poofed away its outsides. And so all of its dust and gas have gone away from it. But they look really pretty, and astronomers originally saw these, and they didn't see it this clearly, and they thought, oh, guys, those look like planets. Let's call them planetary nebulas. And they're wrong, but, you know, the name stuck. Then we get out even further. So, you know, our galaxy, we have neighbor galaxies. The neighbor galaxies we call the local group, and the local group has galaxies like the Milky Way galaxy and the Andromeda galaxy and I should know more of these since it's my mom's research, but I don't. So those are the local group galaxies, and they're about 4 million light years in diameter, and that's our group of galaxies. It's where we live. Then we get out even further, and there are other clusters of galaxies, and some of them are even super clusters, where we have 100 galaxy group clusters. And like the Virgo supercluster, it's in the constellation Virgo. It's why it's called the Virgo supercluster. And it's really very cool, very, very, very many galaxies. And so there are actually billions, hundreds of billions of other galaxies, which is insane. As we expand out even further, we get to the observable universe, and that's the region of space that we can see, that can be observed from the Earth, because light actually takes time to get to us. There's only a certain region of the universe we can actually see. Because again, it takes light time to get to us where we're viewing it. The universe, though, has been expanding since the Big Bang, and we'll learn about that in like 2 or 3 weeks. And so the actual universe is larger than the observable universe, which is pretty cool and pretty crazy. We could think about our cosmic address. We live at Harding in St. Paul in the United States, on planet Earth, in the solar system, in the Orion spiral arm of the Milky Way galaxy, in the local group, which we call the local group kind of like egotistically, really, which is part of the Virgo supercluster, which is part of the Laniakea supercluster, which is part of the observable universe and the whole wide universe. OMG. So I am going to direct you to the next video. This is Powers of 10, and this is a terrible, terrible picture, Ms. Getz. This video is made before you were born, maybe even before your parents were born. It was made before I was born. And the reason I'm having you watch it is that it's just a really powerful reminder of the scale of stuff in the universe. Because it's just insane, the scale of stuff. Not only in terms of location, so you're going to watch this Powers of 10 talking about size of things, but also when you think about time. When we think about things in the universe, they are like millions and billions and trillions of years. that is a huge, you just can't even conceptualize times that large. And so a lot of astronomy that we do is going to be pretty mind boggling, but I think that's one of the